Tonight we're just going to wrap this up with just a brief discussion on solids. There's 5 basic types of solids. These questions tend to be on the question 6 of the AP test. They have not shown up the last couple of years, so it's likely you'll have IMF questions, solid questions. I think it's a pretty good possibility this year. So ionic, we're just going to separate this into units, kind of ranges of forces, how strong they are, and then just some various properties. So an ionic compound obviously is made up of ions. So ions, you might put cation, anion, but just a positive and negative. Okay, cations are positive, anions are negative. Forces, these are ionic bonds, so these are not intermolecular forces, but these are really truly bonds. Okay, they would be known as intramolecular, so between, or no, intra-atomic, I don't know. But these are bonds, not, they're things that actually hold the molecules together, not between molecules. And they have strength in, I don't know, the range of hundreds to thousands of kilojoules per mole. So way stronger than the intermolecular forces we looked at last night. Some properties. They are hard and brittle. So brittle means they crack, they shatter, stuff like that. Hard and brittle, they have really, really high melting and boiling points. High melting point and boiling point. These things also conduct electricity. Conduct, I don't know why I was spelling, conduct heat and electricity. If aqueous, so if we dissolve them, they conduct electricity for sure, and if we melt them down, they conduct heat. Let's see, what else? I think that's basically it. Let's do an example. Probably the most common example would be sodium chloride or just table salt. Okay, and that's true about table salt in all those instances. Our next thing we're going to look at is covalent network, and these things are made up of neutral atoms. So they're made up of covalent bonds, okay, or covalent bonds hold them together. Right, and just like ionic bonds, covalent bonds are super strong. We might call them the 100 to 1,000 kilojoules per mole range. All right, but covalent bonds have really quite different characteristics. They are really the main difference, I guess, is they are non-conductors of heat and electricity. Because their strength is so strong, they are still hard and brittle. And if it's really a covalent network solid, it has really high melting and boiling points as well. So the main difference, I guess the only difference, my bad, is that these are non-conductors as opposed to conductors. And the best example of this is a diamond. All right, and what is a diamond made up of? It is just carbon in a repeating tetrahedral pattern. And each carbon is covalently bonded to 4 other carbons. And you just have this big crystal that builds up, and you have something that's really, really hard. Covalent molecular. These are made up of neutral molecules. Okay, so these are what holds them together. These would be IMFs. Okay, so forces between molecules. So because of that, it drops off to probably the 1 to 50 kilojoules per mole range, depending on what type of intermolecular force is holding it together. And these things have weak attractions, obviously. Instead of being hard and brittle, they're usually classified as soft or flexible. Instead of having high melting and boiling points, they have quite low boiling points and melting points. And again, these things are non-conductors. Notice that both the covalents are non-conductors. All the electrons are being shared. There's no leftover electrons like we have in ionic compounds. So really it's hard for them to conduct electricity. Examples of these things would be wax. What else? Wax is probably the best example. Covalent molecular. And these would be things like water, oils. A lot of these things are liquids because they have such low boiling and melting points. But if it's a solid, wax is a great example. Our next solid is metallic solids. And these are essentially metal ions. In a sea, just like the ocean, in a sea of valence electrons. Alright, and essentially it's basically the metals are just sharing all their electrons. The metals are kind of just floating through all these electrons. The electrons don't really know who they belong to. They're just being shared so liberally. Okay? These would be known as metallic bonds. And you can probably guess metallic bonds are fairly strong again, because metals have fairly high melting and boiling points. So we'll say hard-ish. Okay, high melting boiling points. But what is true about metals? Even though they have high melting and boiling points, if we hit them with a hammer, they don't really shatter and break, so we wouldn't call them brittle. But we have a special word for it. They are malleable. So even though they don't shatter, they're bendable, they're moldable. Okay, so they are malleable, and they do conduct electricity. Okay, so we might say that our covalent moleculars are malleable. Okay, they're soft or flexible, but they're non-conductors, where metallic bonds are conductors, and yet they're still malleable. And then amorphous, just means not or against, would be the Greek prefix. Morph is shape, so it's kind of things without shape. And these are things with really weak IMFs. So they have intermolecular forces, but they're really, 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 really weak. And typically these things are supercooled liquids. Firstly, they're not supercooled liquids, but they're supercooled liquids. With no specific melting or boiling points. And this is, if you had a chance to travel, if you ever go to any kind of old cathedral in Europe, and usually they'll point this out on a tour, but the stained glass windows that they have, if you were to look at, or even if you were to see like an old barn here in the U.S., something that's been around for a while, that has like a piece of plate glass in it, if you look at the glass at the very bottom, it will be thicker than the glass at the top, because that glass, even though it's sticky with itself, it's still flowing, and it's flowing really, 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 really slowly. So just gravity is actually pulling the glass towards the bottom of that window pane. So these things, examples are glasses, or not glasses, I'm wearing glasses, but glass or plastics. Okay, and plastics are the same way. They are really just supercooled liquids. They're in a liquid state, and it kind of depends on the plastic. There's 7 major categories of plastics. PVC, polyvinyl chloride, or high-density polyethylene. But various plastics would be considered amorphous, where others would be covalent molecular. So anyways, 5 main categories of solids. Kind of know the difference between covalent network and covalent molecular. Metallic is in a category of its own, ionics in a category of its own. But to know the difference between these two things, what makes a diamond, as opposed to something like wax, when it's still made up of just non-polar things. Alright, so that is it for the podcast tonight.